Section: Introduction. In this section, we discuss the capabilities of transformer-based language models in various tasks such as natural language generation, reading comprehension, and code synthesis. Despite their strengths, transformers struggle with length generalization, which refers to their ability to handle longer sequences than what they were trained on. This limitation raises the question of whether transformers truly learn algorithms or rely on memorization or shortcuts to solve tasks. Recent studies have highlighted the poor performance of transformers in length generalization across different algorithmic tasks. While some efforts have focused on improving length generalization specifically for tasks like multi-digit addition, these methods may not be applicable to other tasks. Our aim is to develop a technique that can enhance length generalization for any algorithmic task. To address this, we introduce Turing Programs, a novel approach inspired by the operations of a Turing machine, a computational model capable of executing any computable algorithm. Turing programs break down algorithmic tasks into steps, updating a tape at each step by making small changes. By incorporating Turing programs and hard alibi positional encoding, which excels in length generalization for copying tasks, transformers show improved length generalization across a range of algorithmic tasks like addition, multiplication, and simulation of SGD steps. Our method demonstrates significant length generalization improvements, including handling over 100 input tokens for executing random Turing machines. These results represent notable progress in achieving length generalization for multiplication tasks and studying complex algorithms like SGD. We believe that our approach can pave the way for enhanced length generalization in various algorithmic tasks. Section Summary. In this section, we introduce Turing Programs, a novel scratchpad technique inspired by Turing machines, to enhance length generalization of transformers on various algorithmic tasks. By utilizing hard alibi positional encoding, we demonstrate significant improvements in length generalization on tasks like addition, multiplication, and even simulating SGD steps. Our approach showcases the first successful length generalization on multiplication and complex algorithms like SGD, offering a promising method for tackling general algorithmic tasks in the future. Section: Neural Networks and Turing Machines. In this section, we explore how neural networks can be inspired by Turing machines. Many previous studies have created structures based on Turing machines. Some research has proven that RNNs, transformers, and even linear next token predictors are Turing complete under certain conditions. Additionally, some work has focused on understanding the computational capabilities of transformers. For example, Weiss et al. Introduced a human-readable programming language called RASP that transformers can implement. In our study, we investigate whether transformers can generalize the length of any algorithmic task represented by a simple RASP program. We create a basic RASP program that can generate Turing programs to simulate various Turing machines. Moving on to the topic of length generalization, we discuss the issue of handling problem instances of different lengths in sequence modeling tasks. Shorter instances are usually easier to process and require less computational effort, while longer instances are more challenging and demand more computation. Tasks like multi-hop reasoning, program execution, deductive reasoning, and theorem proving fall into this category. Algorithmic reasoning tasks involve input sequences describing tasks, e.g., addition, multiplication, and their corresponding solutions. We assume that the language model can generate many intermediate tokens before providing the final answer. The length generalization problem involves training a language model on inputs of length up to L and then testing it on problems longer than L. We then delve into the concept of scratchpad prompting, a technique that allows models to generate solution steps before producing the final answer. Previous studies have shown that generating step-by-step solutions can significantly enhance the performance of language models on algorithmic tasks. One method we focus on is the scratchpad method, where intermediate algorithm steps are encoded as text and emitted to a buffer called the scratchpad. We revisit the use of scratchpad training to achieve length generalization on algorithmic tasks, considering that it can be viewed as a series of copying operations with slight input modifications at each iteration. By combining the scratchpad technique with suitable positional encoding, we aim to unlock length generalization capabilities. Next, we discuss positional encodings, which are crucial for transformers to handle longer sequences effectively. We review various positional encoding schemes and their impact on length generalization performance. Specific choices for positional encodings known to perform well for length generalization are highlighted, along with a discussion on additional encoding schemes in the appendix. Some models, like decoder-only models with causal attention, can understand positions without explicit positional encoding. Additive positional encodings like alibi and hard alibi have shown promising results for length generalization on different tasks. We particularly focus on the hard alibi positional encoding in our work to enable length generalization on algorithmic tasks, as demonstrated in the following sections. Section Summary. In this section, we explore the concept of length generalization in algorithmic tasks, where shorter instances are easier to process than longer ones. We introduce the scratchpad prompting technique, which involves generating step-by-step solutions before producing the final answer, and discuss various positional encoding methods that impact length generalization. By combining the scratchpad technique with a favorable positional encoding like hard alibi, we aim to enhance length generalization capabilities in algorithmic tasks, as demonstrated in our study. Section: Length generalization on addition. In this section, we discuss the problem of length generalization for addition. We start by reviewing previous findings and the methods they used. We then show that transformers trained with Turing Program scratchpads and hard alibi positional encoding can effectively generalize lengths, even from adding numbers of length 50 to length 100. This is a significant improvement compared to earlier methods that struggled with length generalization. While other studies have reported slightly better results, they often rely on specific input and output formats tailored for multi-digit addition tasks. We may need to discuss these differences in the related work section. Our approach involves using Turing Program scratchpads for addition and presenting our findings on length generalization. For our experiments, we follow a specific format where all steps are combined into one sequence with a separator token between them. The scratchpad format we use is illustrated in a figure in the paper. Our token space consists of 24 symbols, including digits, arithmetic operators, and special tokens. During training, we randomly sample the length of each operand, between 2 and 50, and then sample each digit independently. We train the model by filling the context with multiple independent samples of the task. At test time, we evaluate the models using a sliding window approach to handle long sequences efficiently. Our base model is a transformer with specific architecture and training parameters. We use the Atom W optimizer with a particular weight decay value and no dropout during training. Additionally, we employ hard alibi positional encoding, which includes masked heads and nope heads with a specific hyperparameter setting. The results demonstrate that our approach, combining scratchpad strategy and hard alibi positional encoding, enables transformers to generalize well beyond the lengths seen during training. The model achieves high accuracy, even at length 100, showcasing its robustness in handling different operand lengths. Moreover, our method shows improved stability compared to previous approaches when tested on longer sequences. Section Summary. In this section, we address the length generalization problem for addition by utilizing transformers trained with Turing Program scratchpads and hard alibi positional encoding. By extrapolating from length 50 to length 100 addition, we achieve significant improvement in length generalization performance compared to previous methods, showcasing a remarkable 98% accuracy at length 100. This approach allows for effective generalization beyond the training data lengths, demonstrating robustness even with different initialization seeds. Section: Turing Programs. In this section, we demonstrated that transformers with hard alibi, trained using a specific scratchpad format, can effectively generalize to sequences that are twice as long. By examining the scratchpad in figure Turing prompt addition, we observed that each line is a slightly modified version of the previous one, with minor changes like removing a digit from each operand and updating the intermediate result or carry. The robust length generalization achieved by hard alibi in copying tasks may explain why we outperform previous works that trained models with scratchpads. We propose a generalization of this approach, suggesting that any algorithmic task can be broken down into a sequence of modified copy operations. This concept aligns with the fundamental structure of a Turing machine, a universal computational model. We term this strategy a Turing program. We begin by introducing the standard definition of a Turing machine and then present Turing programs as our scratchpad strategy for achieving length generalization across various algorithmic tasks. Our key theoretical finding is that transformers can execute Turing programs on lengthy input sequences. Turing machines are computational models comprising an infinite tape divided into cells, a head for reading, writing, and moving across the tape, and a set of rules guiding the head based on the symbol read and the machine's current state. Formally, a Turing machine is defined by a quadruple T equals Q, sigma, S, delta, where Q is a set of states, sigma is a set of symbols, S is the initial state, F is the final state, and delta is a transition function determining the next move based on the current state and symbol read. Turing machines are powerful for solving algorithmic tasks due to their universality and ability to solve a wide range of problems efficiently. We illustrate how the Turing machine framework can be leveraged to develop a novel scratchpad strategy enabling length generalization for any algorithmic task. Turing programs serve as a universal scratchpad strategy for achieving length generalization. The simulation of a Turing machine, as depicted in the left panel of the figure, showcases how the state, head, and tape evolve over time. Each step in a Turing machine simulation resembles a scratchpad strategy, where each string is a modified copy of the previous one. We assert that for any algorithmic task solvable by a Turing computable algorithm, there exists a corresponding scratchpad strategy, as demonstrated in the right panel of the figure. Turing programs break down an algorithmic task into a series of intermediate steps, with each step maintaining the machine state. The subsequent step is a modified copy of the previous one, involving minor changes like digit trimming and result updates in arithmetic operations or parameter adjustments in optimization tasks. In the following sections, we showcase how Turing programs can unlock novel length generalization outcomes for complex algorithmic tasks. Section Summary. In this section, we introduce the concept of Turing programs as a scratchpad strategy for achieving length generalization on any algorithmic task. We demonstrate that every algorithmic task can be broken down into a sequence of modified copy operations, akin to the workings of a Turing machine, a universal model of computation. Our main theoretical finding is that transformers can effectively implement Turing programs over extended sequences of inputs, showcasing their versatility in solving algorithmic problems. Section: Theory, Turing Programs in RASP. In this section, we explore the use of Turing programs in RASP to achieve length generalization on various algorithms. We demonstrate that transformers can execute Turing programs over long input sequences in RASP, a programming language that models transformer operations. To ensure length generalization, we adopt a restricted version of RASP that excludes direct index operations. Instead, we utilize n-gram hashing, proposed by Jalasi et al., to enable copying the next state of the Turing machine based on the previous computation. Our approach involves storing n preceding tokens at each position and retrieving the next token based on the matched n-gram. We ensure that inputs do not contain repeated n-grams, which is likely for randomly generated token sequences. Additionally, we require the Turing machine to avoid generating repeated n-grams during processing and perform all operations in memory. Under these conditions, we establish Theorem 4.1, stating that for a Turing machine T that operates in memory without generating repeated n-grams, there exists a RASP program P of size O, n, that accurately simulates T for express n steps on inputs without repeated n-grams. The detailed construction of such RASP programs is provided in the appendix. Expanding on our success with addition tasks and the Turing Programs framework, we demonstrate that transformers enhanced with hard alibi can achieve robust length generalization on complex algorithmic tasks like multiplication with 1-digit and 3-digit operands, linear regression using SGD, and predicting the next state of a random Turing machine. Previous studies have struggled with achieving length generalization on multiplication tasks, with limited success even on pre-trained models. Our experimental setup focuses on fixed-length multiplication tasks, where the first operand varies in length, n, and the second operand is fixed at 1 or 3 digits. We follow a similar setup as in the addition experiments, using a scratchpad format and a specific token space. The Turing program for multiplication is outlined, and we sample digits uniformly for training and testing. Section Summary. In this section, we demonstrate the implementation of Turing programs in RASP to achieve length generalization on various algorithms, particularly showing that transformers can execute Turing programs over long input sequences. By utilizing a restricted version of RASP that excludes direct index operations, we construct a transformer capable of simulating most Turing machines by copying the next state of the machine instead of input strings, based on n-gram hashing mechanisms. This construction ensures efficient execution of Turing programs and enables robust length generalization on complex algorithmic tasks like multiplication and linear regression. Section: Results. In this section, we present our findings on length generalization for multiplication tasks involving n times 1 and n times 3 numbers. We were able to achieve robust length generalization by doubling the number of digits from 50 to 100 for both types of multiplications. It is noteworthy that up to a length of 100, both n times 1 and n times 3 multiplications showed similar performance, with accuracies of 97.1% and 96.8% respectively. This highlights the versatility of our Turing Programs framework. These results were obtained using 7 masked heads and a peak learning rate of 0.0003. The number of heads was selected through a systematic search process, while the learning rates were chosen from a set of options including 7E5, 1E4, and 3E4. Moving on to the training of a model using stochastic gradient descent, SGD, for linear regression, we aim to demonstrate its ability to generalize to different lengths. Given a dataset D equals vec x underscore I, y underscore I equals 0, n1, where vec x underscore I in math BBR squared and y underscore I in math BBR with an initial weight vec w underscore 0 in math BBR caret n, we updated the weights iteratively using the gradient descent formula. For our experiment, we set the learning rate to 0.5 and initialized vec w underscore 0 to 0. To tokenize and prepare the data, we divided the interval -1, 1 into 200 tokens. The model received a sequence of examples, each consisting of 2 input coordinates and 1 output value. It then computed the SGD iterates starting from the last data point to obtain the final weight vector vec w underscore n1. The detailed Turing program for solving SGD can be found in the supplementary material. In our results, we allowed a margin of error in the output predictions and observed that training the transformer model on datasets of size n, LEC 50, enabled it to generalize with over 95% accuracy to datasets of size n equals 80. Our model, hard alibi, utilized 7 masked heads, a context length of 600, and was trained with a peak learning rate of 7E5 for 400,000 steps with a batch size of 16. Additionally, we compared this approach with training a model to directly compute the final answer, which showed a significant decrease in performance. Furthermore, we conducted Turing simulations to test the length generalization of transformers trained to predict the next state of a randomly generated Turing machine. The experimental setup was similar to previous experiments, with a focus on one-step prediction tasks. More details on the data setup and experiments can be found in the supplementary material. Section Summary. In this section, we present our results on length generalization for multiplication tasks using different numbers of digits. We achieved robust generalization by a factor of 2, from 50 to 100 digit numbers, for both single and triple digit multiplications, with similar accuracies around 97%. Our framework, based on Turing programs, demonstrates strong generality up to length 100, utilizing 7 masked heads and a peak learning rate of 0.0003. Section: Results. In this section, we present our findings. We observed that transformers improved with hard alibi can accurately predict the one-step Turing machine transition on tapes that are 2 to 3 times longer than those encountered during training. These transformers were trained with a peak learning rate of 7E5, had 8 masked heads, and a context length of 450. Our experiment indicates that transformers might be able to generalize the length for various Turing programs. However, this does not guarantee successful execution of Turing programs for multiple steps due to potential errors accumulating over time. Nevertheless, we found instances where the machine can execute multiple steps while maintaining high accuracy. Exploring and enhancing transformers' ability to generalize length on algorithmic tasks has been a recent research focus. It has been shown that allowing language models to use scratchpad (COT) data significantly improves their performance on algorithmic tasks. Theoretical studies have also demonstrated that transformers can simulate arbitrary algorithms using COT, making them computationally universal. These results inspire us to investigate whether transformers can learn to execute diverse algorithms effectively. Since algorithms often operate on varying sequence lengths, we use length generalization as a metric to assess the model's understanding of the underlying algorithm. We leverage the observation that transformers can generalize length on the copying operation, which is crucial for executing algorithms. By treating algorithm execution as a series of intelligent copy operations, transformers can achieve significant length generalization performance on a wide range of algorithmic tasks. However, our study does not conclusively prove that transformers can consistently generalize length on any algorithmic task. In some cases, our results show a decline in performance when extrapolating to longer sequence lengths or moving out of distribution. Additionally, our approach relies on extensive COT data, which may not be practical for real-world language model applications. Therefore, we consider our findings as theoretical evidence of the potential for length generalization and suggest that future research focus on developing more practical and robust methods for real-world length generalization tasks.